Excuse me, bouncing? All right, I'll begin. Heavenly Father, we thank you for this day and for tests being over. Just pray that you'd help us to just focus on the remainder of this class, just to do our best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. So you will not find what you need in the book. Not really. I mean, what you should do in terms of studying right now is you should read my chapter 13, all right? In my chapter 13, I give a very simple and basic introduction to vectors in the plane. All right, that's where we're starting with. So, and I'm not going to cover, on the syllabus right now, I have that I'm covering conic sections out of the book. I'm not planning to do that. I did it last time. I didn't find it was very productive. So I'm just going to focus on vectors and then parametric equations and so forth, how to parameterize curves. To give you a summary of what we're doing, basically we're trying to develop some techniques, some tools, and ideas about how do you generally treat curves in 2 dimensions, right? Both the geometry of that and also just the calculus of it. And so we want to go beyond just graphs, right? Graphs have to pass the vertical line test. That's very limiting. We'd also like to be able to describe things like circles or ellipses or hyperbolas or other things which are not graphs, generally speaking. So that brings us to the study of parameterized curves or parametric curves. But to do that, before we even do that though, we really should take a minute or two to talk about vectors, because vectors are the best way to understand geometry in 2 dimensions or more, really. So let's talk about vectors in the plane. I'll try not to be too verbose on this topic. There's always more to do. So, basically, and this is, like I said, it's chapter 13 in the notes I've posted. The title of the chapter is Calculus of Parametrized Curves, but basically here's the thing. If you think about the xy coordinate plane, right? You guys know what a point is, right? Usually P, we might say A comma B, right? And you also know, if I have another point, say Q, C comma D, right? You know you can form a directed line segment from one to the other, right? Maybe you looked at that in high school geometry or something. I don't know if you have or not, but you can. You can do something like, so this is a directed line segment, right? So we usually use so this directed line segment, we use something like PQ with a, well, I think some people call this a harpoon, but basically a vector symbol over it. Now, so that's the directed line segment from P to Q, and that vector is based at P, right? This has base point. Base point P, terminal point Q, right? So of course, this is an interesting idea, right? This directed line segment from one point to another. But the other thing you can do, of course, is you can just talk about vectors from the origin. So another thing I can do is I can associate with P, right? To every point in the plane, I can think about a vector like that, right? And I could call this vector P. Put a vector over it just to emphasize I'm thinking of a directed line segment. And so like, you think about the point P, you think about the vector which points from the origin out to P. What's the relation? If this is the origin is, we just use 0 for the origin, well, you know what that is, what? That's 0 P if you want to use the other notation, right? So it turns out there's a natural way of adding vectors and subtracting them and so forth. Let me just give you the natural geometry, vector addition. Any question? What is it? No. Okay. So, if I have a vector v and I have a vector w, all right, the way we think of adding them is we draw them tip to tail. So the vector v plus w, geometrically, you can picture over here. This vector over here is what we call v plus w. So that's the geometric idea of vector addition. Let's see here. How about if this is v? Where's minus v in this picture? We think of minus v as being the same vector, just kind of flipped over, right? So it's not the same vector anymore. It's the opposite. It goes in the opposite direction, right? So what happens then geometrically if you go, say, vector v, right, plus vector minus v, what happens? So putting them like tip to tail, right, you just get back to where you started again. You just get 0, right? In fact, if you think about the vectors that outline any closed shape, the sum of the side vectors will be 0. Right? For another example of the sum of vectors, which is 0, you could think about this one. So here's A1, A2, A3, A4. Why did I do so many sides? A5, A6 is too late. What's done is done. So A1 plus A2 plus A3 plus A4. I'm still paying the price. A plus A5 plus A6. If you're smart, you take this and translate it into a triangle in your notes. It would capture the same idea. Sorry about that. So I've done all of this just to try to give you a picture of what's the geometric idea of vector addition. How about if we do, how about this? What would A plus A be? A plus A, if there's any justice, should mean what? 2 times A, whatever that means, right? So you can convince yourself pretty quickly that 2A should just be this thing, right? So this is called scalar multiplication by 2. I take the vector A, I multiply by 2, I get another vector in the same direction, twice as long. All right, so these are some of the geometric foundations. Let me just now give you a careful definition. Oh, come on. It's a bad marker day, I tell you. Let's see here, I chose poorly. So definition, ooh, this works. If V is equal to V1, V2, and W is equal to W1, W2, then V plus W is equal to V1 plus W1, V2 plus W2, and also C times a vector is C times V1, C times V1, C times V2. So here's actual definitions of vector addition and scalar multiplication. Excuse me. Let me picture for you also what's going on here. So note, so to get back to the geometry again here, the way this works is like V1, V2, we can rewrite as V1, 0 plus 0, V2, right? That is this definition, and like the geometric side of that would be picturing, well, here's my vector V, all right? And I can picture it in terms of 2 things. I've got one vector down here, which is this piece. So that goes right here to the V1 in the x-coordinate, right? And then I've got another piece over here, 0, V2, which is the y part of the vector. This is the 0, V2 vector. That was the 0, V1 vector. These are the so-called vector components of V. So you can resolve any vector into a sum of its vector components. You can write a vector as a sum of the x vector component plus the y vector component. Which is just a really complicated way of saying that if you want to go anywhere in the plane, you can go so far over horizontally and so far up vertically and get to where you're going. That's all I'm saying. But this geometry here is consistent with this definition of vector addition. All right? All right. Excuse me. So in terms of this, so basically, we also have formulas for this. Like, what's the formula for PQ while we're at this? You can just write this as nothing more than Q minus P, right? I guess if you want me to be fine, I can say vector Q minus vector P if that's less of a... I've defined how to subtract those, I suppose. There you go. So what's vector Q and vector P? This is vector P, right? Where's vector Q? I haven't drawn that one yet, have I? Vector Q is this guy. So if you look at PQ, right? Check it out. PQ, P plus PQ is what? P plus PQ is the same as Q, right? So that's why this formula is legit, right? To find the directed line segment from one point to another, you simply take the difference of the points viewed as vectors, right? So anyway, there's that. Now, what is the length of a vector then? Definition, we use this notation. The length of a vector v is equal to the square root of v1 squared plus v2 squared, given v is equal to v1, v2. While I'm at it, just get it over with here. You can define the dot product of two vectors. V dot w is v1, w1 plus v2, w2. All right. I'm just going to drop some knowledge on you here. This I will derive in Calculus 3, okay? And I'll derive it in more generality, but there's a formula, a beautiful formula, that relates this to the angle between them. The formula is it's the magnitude of v times the magnitude of w times the cosine of the angle between them. So this is just a fantastic formula because it says we can use the dot product to calculate the angle between vectors. This is not that impressive because we're just dealing with two-dimensional problems, but this formula continues to be true in 3 or 4 or 5 dimensions, but not 6. Just kidding. It's good in 60 dimensions or 600, it doesn't matter. Anyway, so, although don't ask me to draw a picture of that. I guess I could. Here. There's 500 dimensional picture right there. So, no, I'm sorry, I'm digressing and being silly. Like I said, I haven't graded your test yet. So, so this is the dot product. That's the angle between vectors. Definition, v is perpendicular to w if the angle between them is 90 degrees. Or, let's see, that's not a good definition. If the dot product is 0. So you could, that would make the 90 degrees between them actually. Or that either of them's a 0 vector will make it perpendicular. All right. So there's a crash course in vectors for you. I should probably work an example, right? Actually, I should introduce something. Let me do an example, and then I'll introduce something. First, example 1 if we have vector v equal to 1, 3, and we have vector w equal to 2 minus 4, find the angle between them. So here's how you do it. What's v dot w? By the way, these angle brackets, this is just a notation to say, hey, I'm a vector. That's all it is, all right? But pretty much they're just the same as the tuples you had like 3 comma 4 or whatever before, you know? And so what we do, the way it works is you multiply x components, so 1 times 2, and then you multiply y components and add them, 3 times minus 4. So this is what? This is 2 minus 12. So the dot product here is minus 10. All right. We also need to calculate the lengths of the vectors. All right. So what's the length of the vector v? Square root of 10. What's the length of the vector w? Man, I don't have one decent working marker with me today. Square root of 2 squared plus minus 4 squared. Square root of, what is that, 4, 16, 20? Yeah. All right. So how does that help you find the angle? Well, you take this data, right? And we notice that v dot w is equal to length of v times the length of w times the cosine of the angle between them. So we can solve for cosine theta, see, because we've excuse me. We know everything there except for cosine theta, right? We know this, we know this, we know this, and we're trying to find that. So solve for it. Cosine theta is equal to v dot w divided by, why am I writing all these symbols? I'm an idiot. Let's see here. So we just figured out what it was, right? Minus 10 is what? The square root of 10, square root of 20, cosine of the angle I don't know yet. So cosine theta is minus 10 over the square root of 200. You go to the trash, you go to the trash. Let's see here. Does this one work? So theta is equal to what? Oh man, look at this. I'm getting worse. So theta, I haven't hit a student yet, which is really something if you think about it. I mean, I've come close to hitting students. I haven't actually hit a student yet, though. Man, these markers are worthless. So this I don't know without a calculator, right? Oh, you're right, I do know that. Just like I planned. Let's see here, 3 pi over 4. Huh, that's true. Thank you. So I can, this is inverse cosine of minus 1 over root 2. Very good. Because the square root of 100 is 10. So, yeah. Yeah. What have I not done here? I found this angle between these two vectors. What did I not even do? And I'm not encouraging this as a general habit, but I'd just like to point out something. I didn't draw a picture. Right? You can calculate the angle between the vectors without so much as drawing a picture. I would encourage you to draw a picture, though, to keep yourself honest. So let's see here. V is what? 1, 3. This is V, right? Where's W point? Over 2, down 4, right? So over to, let's see, up 1, up there. So it's something like that. I can't do it. But apparently this angle here is 3 pi over 4. So my picture's not quite right. I mean, it's a little, well, this should be, I mean, if I extend this back, this should be 45 degrees here, so to speak, right? Because pi would be 180. It's 45 degrees shy of pi. I mean, shy of 180. All right. So anyway, with the dot product, we can calculate the angle between vectors, right? Now, of course, you could use trigonometry to find that angle too, right? And that wouldn't be wrong. But my point is you don't have to do that now. If you know about vectors, you know about the dot product, you can find the angle between vectors in this way. You should definitely be thinking this way in physics. And you're all going to take physics either now. How many people are currently in physics? Oh, so you guys are bored out of your minds right now. How many people not in physics but are going to take it soon? Okay, this is helping you. Sorry for the rest of you. It's too late. Well, I don't know. From what I've heard from the instructors, there's some of you who are taking the course and still don't know these things. So, but that wouldn't be you guys, though. That's not my students. No, not you guys. Other students would do that. Other students. It's really important as a student of physics to try to think in vectors. Don't try to skirt around it. Don't try to find formulas to replace it. You must embrace the concept of a vector if you want to be successful at physics. So that's part of the reason I'm just throwing this into the mix here, also because it gives us just a nice way to write what we're actually after in here. Okay. Now, so the other concept that we should talk about is the so-called standard angle. Right. So if I have a vector, right, a non-zero vector, and it's pointing some direction, say like this, the standard angle is defined to be the counterclockwise angle swept to the vector from the positive x-axis. So this theta is the standard angle. Okay? There's not a universal agreement about what range that should take on. All right? So like, some people would say it goes from 0 to 360. Some people would say it goes from 0 to 2 pi. I'll oscillate back and forth between radians and degrees in here. It's important for you to know both. Other people would say, well, no, the standard angle goes between, it goes from 0 to pi, and then it goes from 0 back to minus pi. So it goes like between plus or minus pi. That's the range of angle, right? I mean, you got choices. And you should choose appropriately to the problem is what it boils down to. And you just got to be aware of the fact that there's a degeneracy here, right? Like 0 degrees is the same as 360. It's the same as 720. It's the same as minus 360. 45 degrees is the same as 405 degrees, right? You can always add a multiple of 360 or subtract multiples of 360 from any angle, and you'll have the same geometric angle, right? So it's important not to be too tied to assuming the angle has to be in a certain range, but you got to be aware of your context, right? Especially with the inverse trig functions, they're only going to give you a certain range of angles, whether or not that's what you should have, right? So you got to be aware of the misleading effect of standard inverse trig functions. Let me get to that in a minute here. Anyway, so we introduce a new notation. We're going to say that the length of v is equal to v. So this is the rule. The vector, we have to write a vector symbol on, all right? If we take the vector symbol off, it's understood to be the magnitude of the vector, all right? That's the usual physics notation. And with that notation, that makes these formulas a lot simpler, right? For example, notice now that we have v dot w equals to vw cosine theta, which is so much nicer to write than what I was writing over there, right? That's one thing. All right, so let's work it out. You can, well, I'll just say you can work it out that this V is basically a theorem. V is equal to V cosine theta, V sine theta. Here, let me draw. Draw the picture where it's least confusing. In the first quadrant here, right? You've got theta, right? The length of the hypotenuse is what? Is V. So what's this down here? Trigonometry says that that's V cosine theta, right? Trigonometry also says that this over here is V sine theta. And so that's all I'm writing here, is that the vector can be rewritten as V times cosine theta, magnitude times cosine theta, magnitude times sine theta. The cool thing is, because of how sine and cosine are defined, these formulas continue to make sense even outside the first quadrant. Right? Like, think about how cosine works. Cosine's negative over here. Sine is positive. Here, sine and cosine are both negative. In the fourth quadrant, you got cosine positive, sine negative. Sort through all that, it's exactly the right signs, SIGNs, to make these formulas make sense in all four quadrants. Anyway, we're going to have a very strong sense of deja vu when we get to polar coordinates, all right? Maybe I should just do it now. Let me just get it out of our system. No, I'm going to stick with it. Polar coordinates are another day. It's very tempting for me to introduce them here, but I'm going to resist. I'm resisting. All right, so here we go. V, check this out though. V cosine theta, V sine theta. What else can we do? Well, we can pull a V out, right? By definition of scalar multiplication, this is V cosine theta times sine theta, right? And what I have written here, this cosine theta sine theta, we can also denote by what's called V hat. So V hat is V over V for provided V is not equal to 0. So V with a hat is a unit vector in the direction of V. So I could also write a vector can be written as V times V hat. This beautiful, simple little formula, what it says is that any vector can be written as a magnitude and a direction. The direction's given to you by the unit vector, and the magnitude is a number that sets how long the vector is. You need those two pieces of information to set up what a vector is. Now, in 2 dimensions, the unit vector is also uniquely prescribed by the angle. This is a special event. In 3 dimensions, you can't do this. Whatever, but we're in 2 dimensions, so we're fine. So I can ask another question here, like going back to example 1, what are the standard angles of V? What's the standard angle of W? Let's work that out. Find the standard angle of V. So what do we have to have? We have to have, well, V is what? V is equal to 1, 3. All right. Come on. Computer's misbehaving. So this is, what do we say the length of it was? This is square root of 10, right? So this would be square root of 10 cosine theta, square root of 10 sine theta, if we believe the theorem. Or more to the point, we're going to have cosine theta is equal to 1 over root 10, and the sine of theta is equal to, what is it, 3 over root 10? These have to be true. Is there anything else that you can say? I mean, here's a comment I might make over here. If V is equal to, let's say, A comma B, and B is not and A is not equal to 0, then B over A, right, is equal to, what is it equal to? It's equal to V sine theta over V cosine theta, which is just what? So the ratio of the y component to the x component should be the tangent of the angle. Right? So you could also look at it that way. Like tangent theta here has to be what? 3 over 1, also known as 3. So is it safe to use tangent here? In the sense, can I use inverse tangent? Is it going to lie to me? What should the angle be here? My question. Where is 3, 1? 1, 3 rather, excuse me. It's like here, right? So I expect this angle theta to be 70 degrees, something like that. I don't know. Anyway, it should be between 0 and 90, right? That's where inverse tangent won't lie to us. So yeah, I can find theta is equal to inverse tangent of 3, whatever that is. And there you go. I could also use inverse sine or inverse cosine. We're in quadrant 1. It's where everything works. Whatever this number is, that will be the same as the inverse cosine of 1 over root 10. It'll be the same number as inverse sine of 3 over root 10. You can't go wrong. Okay? Would you guys tell me what that number is? It's bothering me. Yeah, well, I got 1.249 radians. All right, so maybe. Goodness gracious, will I ever stop coughing? Ay ay ay. Oh, you okay? You say 72 degrees? 72?
That's rounded.
Oh, okay, round approximately 72 degrees. Okay. Let's look at a different example. Find standard angle of V equals to -1, 1. So that one looks like this. Right? Now, if you try to take the tangent inverse of 1 over -1, what do you get? You'll get minus 45 degrees from this. Is that right? So my question here is, we have a vector -1, 1. I try to use the inverse tangent of y over x, which in this case is 1 over -1. The calculator will give me minus 45 degrees. Is that the right standard angle? No. This is clearly false, right? This is the angle we want, right? The calculator is making us think it's over here, isn't it? Right? So that means that the actual theta, the true theta, is 180 minus 45, right? So theta is equal to, what, 135? So this is what I'm trying to warn you about. When you're finding standard angle, you have to beware of the quirks of the inverse trig functions, right? You have to make sure that your angle is actually where it should be. Okay, well, there's your, I just want to give you a brief introduction to vectors so you have some sense geometrically of what they are, what they do for you. Now we're going to move on to calculus. So, and the reason I'm doing this in part is so that we have a better notation for the calculus we're doing here. So what is the calculus of, what's the calculus we're interested in here? So this is the calculus of paths in the plane. So what is a path? What is a path? This is a function from the reals to the plane, like this. In particular, here's a notation, like our vector goes from the reals to the Cartesian product of the reals with itself, or to the plane. So you can think of it in terms of a mapping, like t is a real number, it maps to a pair, x of t and y of t. Right, that. And I guess, fine, to be careful, I shouldn't assume that the domain of a path is the whole reals. We could take like some subset of the reals, all right? So like I, a subset of the reals, all right? So this is for each t in I. I is what we call the domain of the path. Nothing terribly surprising there. So the path is just a function from the reals, or some subset of the reals, to R2. That's a path. It's a pair of real functions, not just one function, okay? So what's the calculus of paths? How would you differentiate a path? How would you integrate a path? Right? So here's the definition. Provided these derivatives exist, we define dr dt to be dx dt, dy dt. Now, if I had devoted more time to this topic, I could dig farther into this, and we could introduce limits here, and I could prove to you theorems about limits of vectors and so forth. But I generally sense a certain animosity students have against limits. So if I don't absolutely need to talk about limits, I tend to shy away from it, in this course anyway. And here's a place I don't technically need to talk about limits. I mean, other people view this as an opportunity to talk about interesting things, but I'm being lazy. Okay, so this is a definition of convenience, all right? There's a more primordial definition, if you will, that you could give. I mean, there's something more basic that you could give here. But this is pragmatic and how you do it. To differentiate a path, you differentiate each component separately. Guess how you integrate a path? Same song and dance. In fact, you can also take a second derivative of a path. Guess what that is? Again, my apologies to the math majors. We could take this as an opportunity to talk about limits for a couple days, and I'm just not doing that. So there's an interpretation here that we should think about. I can draw a picture, right? And this path, R, here it is, R at some time t, right? It's there. Maybe R at t1 is where? Somewhere else, right? At some other time. And what happens? As time goes on, these vectors, they point to different places, right? And so what I'm describing I mean, it could do all kinds of crazy stuff. You know? Here's the path at a later time. All right. Excuse me. We can prove, all right, So what I'm drawing in the red is just the so-called this is the trajectory of the path. What's the trajectory of the path? The trajectory of the path is the point set. It's the set of points in the plane which the path covers. All right? You might say it's the curve. I would also sometimes call it the curve. The path is a parameterization of that curve. Right? If you think about a given curve, there's many different paths which cover it. Anyway, so if I think about t as actual time, right? We usually draw like little arrows on the trajectory to indicate the direction of the motion. That's a new thing. If I give you a circle, right, and I ask you which direction does the circle go, what do you tell me? You should tell me, you're crazy. It's a circle. It's just the set of points such that x squared plus y squared equals to r squared if it's a circle that's centered around the origin, right? Is it clockwise? Is it counterclockwise? We didn't say that, right? But with a path, we have a sense of direction. Because as the parameter increases, t is the parameter, we go a certain direction along the curve. Now, if we're talking about the actual physical position of a body, then this is actually also known as the position. This is the position at time t. In that context, this is what? This is the velocity at time t. And guess what? This down here is the acceleration. So acceleration, velocity, and position are all vectors as we think about them in 2 dimensions. So this is an extension of the discussion you had in Calculus 1 about position, velocity, and acceleration, right? Now they're vectors. I can picture them. The velocity vector points tangent to the path. We'll talk more about this in a future lecture. So like here's the v. This is called v usually in this sort of discussion. I will not try to picture the acceleration vector just now, but here's the v. Over here, v would be something like this. So the velocity vector points in the direction the path is going. I mean, I hope you have some sense of what velocity is, so these are not terribly surprising things I'm telling you, but any questions? So what's the advantage of this path viewpoint? Is it allows us to describe curves which we simply had no access to in terms of y equals f of x thinking, right? Like, for example, I guess it's 4. I don't know. Maybe it's 3, isn't it? I don't know if this numbering means anything. If we look at r of t equal to, let's say, 3 cosine t, 3 sine t, right? Then if you calculate dr dt, you get minus 3 sine t, 3 cosine t, right? And you get d squared r dt squared equals to minus 3 cosine t minus 3 sine t. Notice, so we have x equals to 3 cosine t, right? And we have y is equal to 3 sine t. What happens if you look at x squared plus y squared? Cosine, yeah, we get what? 9 cosine squared plus 9 sine squared, which is just what? 9, right? So what does this say? This says that r of t is on circle, right? Radius 3, centered on origin, right? So we can draw a picture. There's the curve, which this path parameterizes, right? And if I draw r of t, say, like here, I can also draw the velocity, right? The velocity is what? It's going, if sine is positive, right? If sine is positive, then the velocity is negative in the x component, right? And you see, I've already violated my notation, right? You guys should be fussing at me. I won't take off points for you guys, though, if you don't do that. I mean, I'm really open to using both. I actually freely interchange these things. I just view the angle brackets as a way of emphasizing that it's a vector. But I add angle brackets to not angle brackets all day long. It doesn't bother me. Anyway, so these are vectors. Excuse me. Anyway, long story short here, this is the velocity. It's tangent, all right? The velocity is tangent to the circle, right? And where's the acceleration? It's actually minus the position, isn't it? So the acceleration vector here is just, it's inward seeking like this, right? And you can pretty much repeat that picture at every point in the circle, right? Position vector from the origin out to where you are, velocity vector points in the direction you're going, and it just so happens the acceleration vector is always pointing towards the center, right? That's a feature of circular motion. The full story of the acceleration vector I don't think we really give you until Calculus 3, and that's fine. We're just, so our goal, guys, is to really understand this idea that we can take a path, or a curve in 2 dimensions, and we can find functions for x and for y, and use a function x and a function of y in terms of some parameter to describe the curve, rather than just saying everything is y equals f of x. Now we're going to be looking for a function of time for x, a function of time for y, such that both of them together describe some curve. But anyway, I will shut up. Have a good weekend, you guys.